Hey everyone. So today we're going to be looking at some theories surrounding acids and bases. So some other theories besides Arrhenius, as well as a couple of definitions. Um, but to start, just a quick definition. I know we've come across this in the class previously, but as a reminder, neutralization is the combination of an acid and a base. So an acid, remember from our Arrhenius theory, we said that an acid is when it releases protons when dissolved in water, and a base is when it releases hydroxide when it dissolves in water. When those two things dissolve, an acid and a base reacting together, the protons and hydroxide ions will react and form water, um, which should be, I just noticed, a liquid. So it is just pure water in water. An example, stomach acid and antacid tablets. So we see HCl plus AlOH. We have that proton from the HCl, the hydroxide from the AlOH react to make our waters. We have 3 protons here and 3 hydroxides here, which means we're going to get 3 water. And then the remainder is our AlCl3. Because now back to the Arrhenius theory for a second. If you remember, the Arrhenius theory said that when we dissolve an acid, it produces protons, or H3O plus hydronium, and when we dissolve a base, it produces hydroxide, also known or OH minus ions. Okay, so that has some limitations though. So the Arrhenius theory and the limitation on it is that it involves dissolving the acid or base and reacting them in the water. Um, but it couldn't explain the reaction between ammonia gas and hydrogen chloride gas. Okay, so up in the little image there, we see them reacting as liquids, but we can see the steam before they even fully pour it out. You start to see the white substance appear. Okay, and that's the two gases reacting together to create solid ammonium chloride. And the Arrhenius theory, we know this is an acid-base reaction because it neutralizes the two. The NH3 and the HCl become neutralized, but it couldn't be explained because there's no H plus or OH ions being released in this reaction. We're just creating a salt. So a new theory had to be devised, and that is the Bronsted-Lowry theory of acids and bases. So Bronsted-Lowry defined an acid as what they called a proton donor, which is something that can give a hydrogen ion, so a species that can give away its hydrogen ion to another molecule or substance. Okay, so in this case we have our HCl plus water. So if we look at the image here, our hydrogen chloride gas is giving its hydrogen. Okay, we'll learn more proper definitions. Actually, the electron's taking it, but it's donating its hydrogen to the water to become H3O plus. So the water gains one hydrogen to become hydronium, and the HCl lost a hydrogen to become chlorine. Now notice, take a look at the electrons that are shared on the HCl. Okay, when it's shared, one is coming from the chlorine and one is coming from the hydrogen. But when the hydrogen is passed, it's being passed as H plus. Okay, so it's leaving its electron behind. Remember that hydrogen only has one electron. It has one electron and one proton. So if we remove that one electron, all we have left is a proton, which is why we refer to H pluses as protons. So again, it donates the proton, making it an acid. A Bronsted-Lowry base is a proton or hydrogen ion acceptor. So in this case, we have NH3 reacting with water. Okay, the hydrogen from the water here is donated or given to the ammonia. The ammonia is accepting the hydrogen or the proton from the water, making it a base because it's picking up an extra hydrogen to form ammonium and hydroxide on the other side. Okay, so again, an acid is a proton donor. It gives away a proton, and a base is a proton acceptor. So we can define these things a little more clearly. So let's take a look at these two reactions again. Okay, in the first reaction, we have our NH3 reacting with water to produce ammonium and hydroxide. Now we've already established in this reaction that our NH3 is our base, leaving water to be our acid. Okay, now the base, when it picks up a proton, so again, it's only changing by one single proton. That's all it is, just gaining one. If we look at the reverse reaction, okay, let's take a look for a second. Look, so the reverse reaction is NH4 plus OH minus. In the reverse reaction, NH4 plus is acting as an acid, and OH minus is acting as a base. So the NH4 plus is giving away a proton to reform the ammonia, and the OH minus is picking up a proton to reform the water. So when we have a reversible reaction like this, we call these conjugate acid-base pairs. So again, the ammonia picks up a proton. So this would be the conjugate acid of ammonia. So again, conjugate acid-base pairs only differ by a single hydrogen. You know, for water, also has a pair, so this would be the conjugate base of water. Again, because it differs by just one proton or one hydrogen from water. Okay, in the reaction below, same idea. So we have our HCl. We've established previously that HCl is the acid in this reaction because it's giving away a proton to water, making water the base. So water on the other side, okay, when it picks up a proton, so now it becomes the conjugate acid. And our HCl, which lost a proton, so it wasn't acid, it donated its proton away, this Cl minus will be our conjugate base. So again, it's important to remember that the conjugate acid-base pairs, when we make a pair, they're only differing by a proton and nothing else. Everything else remains the same, except it'll have either one more proton if it becomes the conjugate acid, or one less proton if it becomes the conjugate base. Just quickly before we move on here, you'll notice that water in the second example is a base, and water in the first example is an acid. Okay, so there's some substances that can act as both an acid and a base depending on their situation. We call these substances amphiprotic or amphoteric, which we'll see again in a second. But water is an example of an amphiprotic substance. Okay, so look, it's right here. Amphiprotic substances, a molecule or ion that can act as both a Bronsted-Lowry acid or base is known to be amphiprotic. So water is included in that. Amphoteric is a more generic word. So amphoteric encompasses not just Bronsted-Lowry acid-base definitions, but all acid-base definitions. So if something can be an acid or a base under all definitions, it's considered amphoteric. So all amphiprotic substances are amphoteric, but not all amphoteric substances are amphiprotic. Okay, so amphiprotic is a more specific definition. An example besides water, which we just looked at, another example is hydrogen carbonates, or HCO3-. In the first reaction, it acts as an acid, giving its proton away to water, so it donates its proton, acting as a Bronsted-Lowry acid. In the second one, it is accepting a proton from the hydronium ion, so it's acting as a base because it's accepting that extra proton. So in this, just as a reminder from the previous slide, here we have our hydrogen carbonate acid. This would be the conjugate base. Here we have our hydrogen carbonate acting as a base, which means this would be the conjugate acid. Again, water has its own pairing as well. Some substances, such as amino acids, can actually act as simultaneously as a base and an acid. So they are still amphiprotic, but we call this a Zwitter ion. So this side here can actually give away a proton. It has an extra one to give, and this COO minus has a place to accept a proton. A couple of more definitions. So the number of hydrogens. Some substances, hydrochloric acid, for example, has one hydrogen. Sulfuric acid has two hydrogens, and phosphoric acid has three. Okay, so these acids can be referred to as being monoprotic, diprotic, or triprotic, depending on how many hydrogens they can give away. It is important to note, though, that not all of the hydrogens are equal. For example, on sulfuric acid, it will very readily give away its first hydrogen, but it's a little more difficult for it to give away the second one. And those are properties we're going to look at when we study the more advanced section of acids and bases. We can have strong and weak acids and bases. Okay, so a strong acid is an acid that undergoes complete dissociation. So it completely splits into, so for example, in the above here, we see our HCl. So HCl completely splits. So if we have 10 molecules of HCl, all 10 of them will split into H and Cl minus. Okay, so that's a strong acid. So whatever we have at the beginning, that's what it splits into on the other side. So we call that dissociation. A weak acid only undergoes partial dissociation. So we see down here our phosphoric acid, we have an equilibrium. Okay, so if we start with 10 molecules of phosphoric acid, perhaps only 5 of them dissociate. Okay, so then we would be left with 5 on the reactant side and 5 on the product side, or we'd have to look at the stoichiometric ratios. So weak acids are in an equilibrium reaction. So that is going the forward and reverse reaction going back and forth constantly. Okay, lastly, here are some common acids that you should know. These are ones you should know, you should recognize, know them off the top of your head. Okay, so we have hydrochloric, okay, nitric, sulfuric. I'll let you guys look at the list of these. One important thing to know is when we talk strong and weak acids, these ones highlighted in green here, these are the strong acids that you should know. So hydrochloric, nitric, and sulfuric. The 4 down the bottom, those are weak acids. And you'll notice something that a few of them have in common. So carbonic and phosphoric are weak, but the ethanoic and the benzoic both have that carboxylic acid group. So anytime you see the carboxylic acid functional group, or you see something with the ending oic acid, you can generally assume that that's going to be a weak acid. And here are some common bases that you should recognize. Same as with acids, we can have strong and weak versions. The ones highlighted in green here are the strong versions, or the strong bases. Okay, and the ones below, ammonia and ethanamine, are the weak bases. The strong bases, you'll notice that most of them are simply group 1 or 2 metals with hydroxide added onto them. So if you see a group 1 or 2 metal with hydroxide, that is a strong base. Okay, a weak base is recognizable by having an amine group on it. So here's amine by itself, or ammonia, or ethanamine has this NH2. So anytime we see that amine group on a substance, we can generally assume that it is a weak base. Okay, and that's all for the definitions and Bronsted-Lowry theory of acids and bases.